Thank you for joining us for Science and the Solar Eclipse. I'm your host, Gordon Dickson. We'll be talking to Dr. George Matzko about the upcoming solar eclipses here in 2024, 2026, 2028, and 2030. The solar eclipse in 2024 will pass across the midsection of the United States. The 2026 solar eclipse will pass from Greenland down through the midsection of Spain, and the eclipses in 2028 and 2030 will crisscross over Australia. Thank you very much for joining us today on the broadcast. We are talking with Dr. George Matzko, and one of the reasons that we're discussing this with him is he has a PhD in analytical chemistry, and it is fascinating to think about what is getting ready to happen with several eclipses, solar eclipses that are going to occur here on Earth over the next few years. And so we wanted to talk it over with Dr. Matzko and get his ideas and understanding, help get his explanation for us in layman's terms of what we're actually seeing. So Dr. Matzko, thank you very much for joining us on the broadcast.
Pleasure to be here.
Tell us a little bit about your background and especially what is analytical chemistry. You have a PhD in analytical chemistry from Clemson University. Am I thinking correctly there?
That's right. So analytical chemistry is kind of a hands-on type of chemistry where you are analyzing things both for what they are and how much is there. So it's very important, especially in manufacturing, to know what ingredients you have and the proportion of ingredients that you have. And so they used to call it manufacturing chemistry because it's a very practical form of chemistry. And my research involved being able to detect drugs of abuse in biological fluids. This is a long time ago. Now we're talking about the mid-1970s. Back in the 1960s, there had been some really terrible truck accidents and bus accidents where people were high on drugs, if you remember the drug culture back then. And so the public was up in arms and they wanted some way to make sure this didn't happen again. And so we would test different drugs of abuse, see if we could see them in biological fluids. My particular research involved high-performance liquid chromatography with electrochemical detection, and I would spike my own urine with things like LSD, and then I'd see if I could extract it back out and be able to see how much was in there. And so these type of tests became standard later on.
Yeah, I can see how practical that is today. It's almost routine now in every office, and especially in manufacturing places, to have that kind of analytical chemistry today. So that kind of leads us right into our discussion because we're talking about solar eclipses. And I know that most people on a day when the sun is shining, you say, hey, the sun is shining. And everybody's like, sure, but let a solar eclipse come along and everybody wants to study the sun. So what do we know about the chemistry of the sun and how have solar eclipses helped us to gain that understanding?
So the sun primarily consists of hydrogen and helium. They make up about 98% of its total mass. These elements are products of nuclear fusion processes that occur within the sun's core. There are some trace elements, though, and so in the past, there have been those who have been able to use solar eclipses to actually determine what other elements were in the sun. I think it was Henry Augustus Rowland who produced a modern map, essentially a modern map of the solar spectrum. He identified 36 elements present in the sun. I think that was in 1873. And the other elements that are prevalent are things like oxygen, which is almost 1%, carbon, about 0.4%, and then a lot of trace elements like nitrogen, silicon, magnesium, neon, iron, and sulfur.
And at the time, back in the 1800s, what kind of instruments would they have used to determine that those elements were there?
So they would use the refraction. They would use prisms. I don't know about Rowland himself, but I understand some of his colleagues, they would set up a prism, and they would be in a black room. They'd have a room that was completely painted black, and the light from the sun would go through the prism, and they would get various line spectra that were characteristic of these different elements. And by doing it during a solar eclipse, they could actually see how the elemental composition changed in different parts of the sun.
I see. And so, with your background in analytical chemistry, when that prism, when the light divided in that prism and showed up, like you said, in a black room, is it because the various elements actually manifest in different colors?
That's right. So each element has a different electronic orbitals, and the electrons jump from one orbit to another. And we can actually see that difference between two different orbitals, and that manifests itself as a particular wavelength of light. And so we still use that today. When you see that NASA says that a certain exoplanet has this composition or whatever, they're doing the same kind of thing. They're not using prisms made of glass anymore. They're usually using diffraction gratings, but the principle's the same. They're actually dividing up the light, looking at the particular lines that are characteristic of that particular element.
And so, as we look back at history and we see the number of times that a new understanding of the sun came about as a result of the eclipse, that's one of the things that makes eclipses so fascinating is what are we going to discover this time? And there's really some fascinating history behind that. You mentioned Henry Augustus Rowland and producing that map. I remember, I want to say it was Jules Janssen and another man named Joseph Lockyer. They actually, if I remember correctly, they actually discovered helium during an eclipse back during that same period.
You can tell from the name helium that it's named for the sun, Helios, right? The name
Right.
for the sun.
Mm-hmm.
And so helium was discovered in the sun before it was discovered on Earth.
Isn't that amazing? In the sun before it was discovered on Earth. That is really fascinating when you stop to think about what might we discover this time, in a solar eclipse. So that really makes it part of the adventure every time we have a solar eclipse like the ones we're going to have. So let's go back just for a minute and talk about what is light. I know it sounds pretty basic, but when you get right down to it, what is light? How would you describe light?
So light is a form of electromagnetic radiation that's visible to the human eye. It consists of particles called photons, which have properties of both waves and particles. Light travels in a straight line until it interacts with matter. At that point, it can be absorbed, reflected, or refracted. It encompasses a range of wavelengths, from shorter wavelengths such as ultraviolet and blue light to longer wavelengths such as infrared and red light. And of course, light plays a crucial role in our perception of the world and is used in many different scientific fields as optics, physics, astronomy, and analytical chemistry for that matter.
Now, I remember back in high school science class, they talked about this, and there was a discussion at the time about whether or not light was in waves or was it in packets that I remember them calling photons. And so what kind of developments have we had in that area? Do we understand light any better than we did back in those days?
So the answer is yes. It's both waves and particles. It has a dual nature. As Christians, we should be used to the idea of a dual nature, right? We talk about Jesus Christ was all man and all God. And so 100% man, 100% God. And that's a dual nature. Well, same thing applies to light. It's 100% waves, 100% particles.
And so when they talk about these particles, the particles are moving in wavelengths. Am I thinking correctly there?
No, you have to think about what particular experiment they're doing. There's some experiments you can do that you take advantage of the particulate nature of light, and some experiments you can do that actually measure the waves of light, and it acts as a wave. It can cancel itself out. It can be refracted. You can have light and dark patterns. You can shine the light through what we call a double slit, and it'll act as a wave on the other side.
In Stephen Hawking's Brief History of Time, I remember reading about that very experiment, and I remember that was really fascinating.
It depends on the experiment that you're doing, whether light acts as a wave or acts as a particle. It's going to be one or the other. It's not going to be both at the same time.
That is fascinating.
Then you think about Jesus, on Earth. I mean, his dual nature. Here he's asleep in the boat, and he's acting as a man. He's tired. He's in the boat. And then he wakes up. The disciples say, "Don't you care that we're perishing?" He wakes up and he acts as God, calming the winds and the waves. So it depends on what's happening, whether he's acting as a man or acting as God.
This is where it really gets interesting, because you and I have been talking this over quite a bit, as far as when the moon passes over the sun, it's like in its hiddenness, the fact that the moon is passing over the sun, that's been the place at which we have learned so many things about the sun, about its outshining glory, its chemistry, those kind of things. It's really fascinating to think about what you are describing with Jesus Christ, the Son of God, becoming a man, and in essence, bringing it down to a human level that we could understand, almost in the very same way that the moon has passed over the sun, and we've discovered things like helium from Helios, like you were talking about a few moments ago. There's a fascinating parallel there that we probably ought to explore just a little bit more. So how does light function, visible light, how does that function on the electromagnetic spectrum?
Well, if you think about light, when we talk to the kids about light, we say there's light you can see and light you can't see. Of course, there's light that animals can see that we can't see. Pit viper, like the rattlesnake, can see infrared, and we can't.
And we want to come back to this in our next broadcast as we think about the nature of light, and especially in terms of the eclipse. We hope that you'll join us for the next broadcast as we come back to talk to Dr. George Matzko. Dr. Matzko, thank you very much for being on the broadcast with us today.
Thank you. It's a pleasure.
Thank you again for joining us for these series of conversations with Dr. George Matzko. He can be reached at his website, georgematzko.com. That's GeorgeMatzko.com. The Matzko Science Ambassadors. These broadcasts are brought to you by LiveServeLead.com. Live, Serve, Lead, helping others succeed.